Alright, kiddos, we are going to be taking a look at the periodic table right now, and I just wanted to show you some patterns that exist within the periodic table. Um, so the first thing we're going to notice is that we have these 7 different periods on the periodic table, and the reason that they're periods is because we have these repeatable patterns. So in a simple class day, our school has 7 periods a day. So you do one period and then things kind of start over. You do the next, then you do the next, then you do the next. So the same is true with the periodic table. We have this repeating pattern. Now there are some patterns that will change as we move down, but there are also some things that are kind of repeating, and we're going to look at why that would happen based on electrons within each atom. So let's talk about hydrogen to start. So when I hover over this, you're going to see this gives me some information. This gives me the atomic number, the average atomic mass of these atoms, and it also gives me the number of electrons because I've asked it to give me that. That right there lets us do that. So right now we see we have 1 proton and 1 electron, and this makes sense hopefully to you because we've got a neutral atom of hydrogen. And what this is telling you is that we have 1 positively charged particle, the proton, and 1 negatively charged particle, the electron. And any time we're looking at any of these elements on the periodic table, if we're talking about a neutral atom, we would expect to see the same total number of electrons that we have protons. If we go over to helium, we're going to see that helium has 2, whoops, come on, stay there. It's not going to stay. Okay, so you're going to have to look at the big blue image of helium on the left-hand side of the screen. Helium has 2 protons, and that's why the atomic number is 2. And it also has 2 electrons. So again, a neutral atom in this scenario. Now, these 2 things behave insanely different. Hydrogen is extremely flammable. Helium is relatively not reactive. So the reason for this, hydrogen has only 1 of the 2 electrons that can fit in this first orbital. Only 1 of those electrons is there. This has both. So this does not need anything. It's already filled that electron shell. And this needs something. And it can either get rid of that one or it could gain another by combining with another material. So this makes hydrogen reactive. If we scroll down and look at all of these elements, you're going to notice that the bottom number out of all the electrons is always going to be 1. What this is telling you is that it only has 1 electron in its valence shell, so its outer electron shell, the thing that's furthest out and most likely to interact with other materials. So all of these just have 1 thing that they need to get rid of. So when we look at these materials, they're crazy psychotic. The alkali metals are really, really reactive, and the reason they're so reactive is because all of these have that 1 electron in the valence shell. Now, if we look at these materials, these are our noble gases. All of these have a completely full valence shell. What this means is that there's no space for any more electrons. They're all full. They're totally satisfied. So even if they could think for themselves and said, hey, I really want to combine with something else, they're going to have a really difficult time doing that. Now there are some compounds of xenon that exist. I don't know how that happens exactly, but there have been some xenon compounds found. But these things in general are like pulling teeth to get them to react with anything else. They're very, very stable, and the reason for that is they don't need to combine. If we look at the pattern in this 17th group here, group 17, you'll see that all of these have 7 electrons. So these are our halogens, and these are fairly reactive. For being on this side of the periodic table, they're pretty reactive, and the reason they're pretty reactive is they really need to gain 1 electron to fill their valence shell, and that's going to affect how they behave as well. So I'd like to show you what I mean when I'm saying reactive. We're going to go to this potassium video. It may take me a second to find the exact explosion. But potassium, this is just potassium in water, and this is how bad potassium wants to take care of the fact that it's got this one extra electron in its valence shell. So if we scroll forward here, we're going to see this creepy guy's face. He's very handsome. I didn't mean to call him creepy. And then we're going to see a video
unreacted potassium
of them dropping potassium in.
Oh, wicked.
Now, to us watching, we say, wow, that's pretty cool. You know, we got a little explosion just from dropping something into water. Well, what's happening there is it's trying to lose that valence electron. It's trying to combine with another material, so it's highly reactive because it doesn't want to just have that one valence electron there. We'll look at rubidium as well, and this is not as explosive as I would like, but you can see they're trying. These guys are definitely respecting the material. So rubidium here, we drop it in.
That too.
It doesn't all react.
Was that it?
Was that it? So they were expecting it to be more reactive than it actually was. There's a video on YouTube of someone dropping cesium into a bathtub. But we'll watch this anyhow. Cesium is, again, it has that one valence electron, so it is highly reactive. So these guys are being safe. You can see, we'll let this go here. And
quite a spectacular reaction.
Quite a spectacular reaction. So we've obviously got cesium being highly reactive as well. Francium is really hard to get a large sample of because it is so reactive. It doesn't really exist that often in nature. So if we compared this with these things, you would watch the entire video. You would never see any reaction with any of these. They would just talk about all the cool ways that they're used and all that good stuff. If we scroll over, we're going to see similar patterns. So within every group on the periodic table, group 12, for example, you know, all of these have 2 valence electrons in this group right here. Copper, silver, and gold, 3 of the best electrical conductors there are on the planet, all have 1 valence electron, but because the valence electron is not in this, the s orbital, which probably doesn't make sense to you right now, but because the valence electrons are located in kind of a more secure orbital, this just makes them really, really good conductors because they're willing to kind of allow those electrons to move freely. So main thing I wanted you to see with this is that there are patterns within the periodic table in terms of our electron structure. Hopefully you're seeing that and you can explore it yourself to think about it a little bit more. And that also these patterns have a major impact on how the materials behave. So how these elements behave is really based upon the simple fact that their electron structures are very different. And if they need to lose an electron to have a completely full valence shell, then they're going to do that, and they're going to react to do that. And if they already have that completely full, they're going to be way less reactive. And then you've got this wide gamut in between of patterns within the valence electrons that are going to allow you to see some different behaviors amongst the periodic table. Hope this is helpful to you. Hope that makes sense. Feel free to ask questions, and I highly, highly encourage you to explore ptable.com. You can do a lot of great stuff with this. Not only can you check out the actual electron orbitals and what their shapes would be, you can see their shapes right here. You can also watch some cool videos if you go to this tab and scroll down to the videos. And if you're curious what any elements look like, you can also look at the photos. So have fun with that. Let me know if you have any questions. Thanks.